Hello and welcome back to Calculus 2, section 6.3, volume by slicing, but it's actually disk and washer method. The first part of this lecture I usually skip because far more powerful techniques in Calc 3 are coming up, so it's not necessary for us to really go through it. We're focusing on disk and the washer method because those two methods are unique and they're not done anywhere else in a better way. I mean, volume occupies 3D space, right? Area occupies 2D space. So in order for us to understand these things, we first have to understand the space we are talking about. And the number of dimensions determines the space you're talking about. A point is a location. It exists in all dimensions. You can have one dimension, which is just length. So this is 1D, and it's just length. And then you can have, let's say, a square, which is 2D, and that's going to be area. You see, you can color in the square, you cannot color in the line. The line is just length. And then you can have a cube, which is 3D, which has volume. Now, it also has a surface area, and the area 2D has length of each side, so each next dimension assumes and uses all the previous ones. You can have 4 dimensions, which is what we use most of the time, because you have 3 dimensions for space and 1 dimension for time, call that space-time. But then you can also, you will see in Calc 3, use the 4th dimension frequently because you can describe the object in terms of its bounds using 3 dimensions, and then use the 4th one to either be the density or distribution, or to be the temperature within the object, and so on. So the number of dimensions is actually just the number of variables that you are using. And if you haven't taken linear algebra yet, but you will see that you can work in any frame like dimensions, on every number of dimensions that is necessary for the problem. In terms of engineering, clearly you are building something mechanical engineering, it's going to be 3D, right? Unless you are talking about how the object behaves when heated or under stress or something like that, then becomes the 4th dimension is whatever you are observing within that 3D object. So the number of dimensions is going to be very important. Now, we already said that area is the integral a to b of f minus g dx, where I said that this provides the height and this provides the length, and when you multiply them together, height times length equals the area, right? So I know that this is a 2-dimensional concept because 2 dimensions. And now we are moving to volume. I would like to calculate volume of specific objects. We all know that we can find the volume of this room we are sitting in by simply multiplying length times, right, width times the height, and that gives us the volume of the room. But what's the volume of this bottle? Even simpler, what's the volume of this cylinder, right? I'm holding the container for these disinfecting wipes that are 99.9% effective. So how do I find volume of this? Now, can anyone spot the commonality between these two objects? Circle when you cut it in the right way. We are going to talk about figuring out the volume of objects that you obtain using rotation. if I graph on this XY graph, if I graph a line segment and I rotate that line segment around x-axis, what will happen? What object it is going to create? It is going to create a cylinder, because it will rotate again. It will be 2 units away from the x-axis, and since it's rotating, it is going to create a cylinder. So a straight line, and guys, you see that straight line on the top of this object. That straight line is going to create, once you start rotating that line around x-axis, it's going to create a cylinder, right? We know that this function here, f of x, is equal to, let's say, 2, because I went 2 units up. So if I rotate 2 on 0 to 7 or whatever it is, let's say I'm getting this shape. I'm getting this object, right? What am I going to get when I rotate this? Nope. If I rotate a semicircle, it's going to be a sphere. I'm getting a football, exactly. Right? If I rotate this, I'm getting a football. That's a light bulb, exactly. I know. Or a pear. I don't care, right? It's going to be something. That's an old-fashioned light bulb. Baseball bat, right? As long as you're able to mathematically define the function, you can program that into the machine, which will bring the knife and carve whatever you want out of wood, metal, plastic, or whatever you do. All those football guys think they're tough. You know what? I want to make the ball out of solid lead. See how well they do. They think they're tough, right? What is common for all of these objects? All of them. The thing that is common is that when you take that object and turn it this way, no matter where you cut, you will have a circle. Goes for that clock as well. If I take that clock off the wall, face it towards you and cut it this way, it's going to be a circle underneath. It goes for this object as well, minus the nozzle on top, because if I cut it here, it's going to be a circle, smaller radius than this one, and all of these circles will have the same because that's the cylinder, right? So all of the objects, a marker, right? Also the same thing. Kevin, can you lift your bottle all the way up? There it is, another one, right? And the coffee cup over there as well, right? That one. The coffee cup? Of course, we're modeling now. That coffee cup, what do we have to thank you? What are we rotating to get the coffee cup? What are we rotating? A line segment. See? You rotate this around the x-axis, you get the same line segment on the other side, and coffee cup. Right? So you got to be able to visually see these things. Once you're able to visualize these things, then setting up the integral will be easy because you will remember the formula, which I will explain. And then it goes down to modeling. It goes down to modeling. So now what do we have for the famous disk method? It's clearly called the disk because every time you cut a little slice, it's a disk. Like your Blu-ray discs. You still use DVDs, anyone? You know what those are, right? All right. Never sure, you know, how far back. Like if I say a CD, probably no one knows what the hell I'm talking about already, right? Huh?
VCR.
You have a VCR?
Yeah.
Yeah, it's not going to be by rotation on that one. It's a brick that goes in. But yeah, I have over 300 LPs, but that's something going to be like yeah. See? There we go. What I was talking about? Oh, yes. So, volume. It's pi a to b fx squared dx. And here's your cloud. So this will have 2 videos, but that's okay. All right. So this part here is my function, which goes and is going to be squared. Here's my dx that I was talking about, which travels from A to B. Yes?
Why did you draw the dx there? Would it be extended to underneath the axis too, or just has to
No.
be the top half?
It would just be the top half from x-axis to the, and I'll explain that. I'm just waiting for everyone to stop writing because it's extremely important for everyone to see this part now. So, do you remember how the volume is area times the height of the object? So area of the base times the height. Do we remember that? What's the area for the circle?
Pi r squared.
Beautiful. And then times the area h to get the cylinder, right? Now, observe the screen. Pi r squared times the height. You see that the height is actually now on x-axis because this object is going to be this way, right? So the height of the object is actually the length, which is dx, travels from A to B. That's your height. You see that this object is round, and here's the answer to your question. It's the radius that is squared. It will be a diameter if I go this way, right? So it's radius squared. It goes from x-axis to the function, which is just the function, right? From 0 to function. This makes so much sense to me. I don't know. You'll figure it out eventually. So one more time. I have the radius, which is my dx, stretching from the axis of rotation to the function, and that radius is the function because that's the function above the x-axis. We are pi for pi r squared, and we have our dx from A to B, which is the height of the object. Once I create this cup, I'm going to stand it up. So all I did is I took this formula here, and I replaced r with f of x, and I replaced h with dx. And that's it. That's all of the wisdom for the method. Now what happens next? The next is well, computing is Calc 1, right? The next is the discussion on dimensions. I'm claiming this is volume. Is it volume? Of course it's volume. I have y times x. You see, I have f of x, that's y. I have another f of x, that's a y. And then I have dx, which is x, from a to b. So that's 1, 2, 3 dimensions. So this is 3D, which is volume. You also have to make sure that this makes sense dimension-wise. So now you have this formula, and then you realize that you can also rotate around y-axis. So now I can come up with, I don't know, let's say function like this, and if I rotate that on the y-axis, it will look like this. It will be some kind of dish that has a spike on the bottom, and you have to balance it, I don't know, to stand, whatever. Volume in the y direction is pi c to d of f of y squared dy. So we can also rotate around y. Now I usually put rotation around y with the formula, and then over here I will say rotation around x. So go back, add the rotation around x, and then on the bottom formula for the y direction, rotation around y, make sure your integral goes from c to d, because that's y1 and y2. So here's your c, here's your d, and here's your function x equals f of y. You will have to quickly realize these things, that x is f of y and y is f of x, right? Should be common sense by now. So now, examples and problems. Find the volume for f of x equals x squared on 0 to 1. Rotating around x-axis. So we draw. X squared on 0 to 1 looks like this. And when I rotate on the x-axis, we're going to get the other one. So I'm getting the same shape that I drew before, and now it's except it's on x-axis. The volume on this one is what? Let's set it up. What should I write? Pi. Beautiful. X squared squared, nice. Dx. X squared is a function, and you have to square it. It's usually a troll question for the exam, right? You forget the second square. The formula has a square, so square, right? So you're integrating x to the 4th, that's x to the 5 over 5. Plug in the numbers, and clearly pi over 5, good. Just by looking at it, pi over 5. Go on, computer. Oh, you have the object that you cannot compute. Nice. Better show that one too. Guys, here's the object that you cannot compute using this method. It's not circle, right? It's square.
5?
Yep.
All right, so let's pick some of your favorite functions and stuff, so it's not just bland and boring. So here it is. Go. We all have the same setup, right? Then fix it. We all have the same algebra, right? Are we good on this?
I got a quick question.
Yes.
Aren't you wrong about like e to negative 2x? It gotta be like negative 2 is not always underneath negative 2?
Well, the integral of e to the negative x is...
E to negative 2x is like e to negative 2x, and you gotta multiply it by 2.
The formula for e to the x integration is integral of e to the ax dx is e to the ax over a plus c. Now that a could be negative 2, could be positive 100. It's just gonna be copied in denominator as is.
Okay, well I'm thinking probably from derivative, where you did.
Oh yes, the derivative multiplies. Integral divides.
Okay.
Same for sine and cosine. Integral of sine 2x is going to be negative cosine 2x over 2.
Okay. And how you get the ln 1 over 16 anyways?
That's 4 to negative 2. The exponent goes, the negative 2 goes in as the exponent of
Yeah, it's like
4.
Would that be ln 16 then?
No, it will be ln of, it's not 4 squared, it's 4 to the negative 2. Negative 2 brings it in the denominator.
Or is it negative 2?
So it's like 1 over 4 squared. 1 squared is 1, and then the denominator 4 squared is 16.
Yeah.
No,
The formula 1 over, no, x to the negative n is 1 over x to the n.
okay.
So that was 4 to negative 2, which is 1 over 4 squared, which is 1 over 16.
Okay.
Is this stream dying again? No. And by popular demand, we are going to do one of the trig problems. I know you waited a long time for this. How do we integrate this?
You want to do the chain rule.
Don't chain rule.
1 plus cosine 2x.
Yep. The power reducing formula. The only way you can integrate this is power reducing formula. If you don't know it, doom. This is why I listed it yesterday in that review and told you make sure you know it. When these squares, and there will be a lot more of this in chapter 7, popping up sine squared and cosine squared. You must know this conversion formula, which was listed yesterday. And there's one for sine, which looks the same, except there's a minus sign. So sine squared is 1 minus cosine 2x over 2.
Can you also do the U substitution as well?
Well, now we will have to, well, you can use U substitution now, but we also can just skip right in the answer. Integral of cosine is positive sine. Pi over 2 times 2 is pi, sine of pi is 0. Yep, I'm just waiting for everyone to get. All right. So now, let's see. So this is the first half. There's one more formula that does the same thing. Remember how you have area under the curve and then area between two curves? If you rotate the area under the curve, which is technically this, you are getting the volume of the shape, right? So now we can have this between two curves. Same calculations, same everything. The formula changes a little bit, and it's the same jump like you have from one curve to two curves. So let's say that you have a square root function and a linear line. That will create this area in between. The top one is f, the bottom one is g, and we are rotating again on x-axis. Now this is going to create a shape that has a hole inside, right? It's a hollow inside. So the volume for such shape is again a to b, or pi in front, a to b, and then you have f squared minus g squared dx.
May I ask, with all these formulas, how will you be able to determine which one you have to use?
Yeah, when you see the shape, right?
Okay.
Because this one has two functions, so it has to be this one. The previous one had one function, so it has to be the other formula, right? Again, far away minus close by. This method is called washer method. And it's called the washer because anytime you get the shape and you cut it, you're getting washers. You know what the washers are, right? It's that metal ring with a hole inside. That's a washer. So this is called the washer method. It's for hollow objects, maybe the cap of this marker, right? It has the inner function and the outer function, and if you are to cut this object, you will get the washer. Now, CD is a washer, right? And you have one for Y direction as well. The proof for this is identical to the proof when I said banana, right? To throw away the peel and use the rest. So if you find the volume of the outer, and then you find the volume of the inner, and then outer minus inner is exactly the leftover. So now we have a lot of beautiful examples for this. It doesn't look like we can do the next section tonight, so we'll just continue tomorrow. So we'll do 6-4, 6-5. We'll see how well with 6-6. Maybe we get to venture into 6-6. You have y equals 4th root of x and y equal x intersecting, rotation on x-axis. And anytime you have two functions, you are responsible to figure out the limits of integration by setting equations equal to each other. Just like we did for area between two curves. So, set up, and then far away minus close by, square each one individually, obviously. Yes?
I got a quick question. I want to do x equals fourth root of x. I don't know why I said that. So, do I...
Set these equal to each other?
Yep. Subtract 50x.
No, you form a power of each side, and then you set this. You have to get given the form root.
Yep.
So you do the opposite operation, form power. And then you subtract x and factor x and get the rest of the line.
So when we set these guys equal to each other, we have the fourth root of x equal x. We apply fourth power to both sides and get x equals x to the fourth. And then we put them together and we factor x. And we get x is 0 and x is 1. So now we are able to set up far away minus close by.
Just got a quick question. Basically, isn't it y equals x the father? You said the father
from the axis of rotation. So if you look at it this way, right?
Yep. Okay.
So x to the 4 is far, so far minus close, right? All right. Y equals 0. Y equal ln x. Y equal 2. X equals 0. Rotation on y. So try to graph this without, like, first you have to graph it, use all of the bounds to find the region, and then you'll see what happens.
Line, done.
What I got here, so what I got here is like ln of x, whatever it goes out, like that. Yeah, I can tell them. dy. So if I'm on this, what? So, but you can't multiply the ln of y term in content. Like, we have been taught whatsoever, or when I was a little kid, we have been taught to do that. Divide ln, how we used to do that. For x.
No, there's no.
haven't taught that.
How do you put X on the
You multiply each side by X. Do ln y. E on, oh yeah, e to the X.
Yep. All right, so we graph this first. We have y equals 0, y equal 2, y equal ln, and x equals 0, which creates this region here. And then we rotate that on y-axis. When we rotate this on y-axis, as soon as it's a y rotation, it must be dy. We see the limits are 0 to 2, so volume has to be pi 0 to 2, but since I am using dy, I cannot put ln x there. So I have to take the function and solve it for x, which means e both sides, and from there x is equal to e to the y. So that's the one that goes in here. So further, that's pi integral 0 to 2 of e to the 2y dy, which is pi e to the 2y over 2 from 0 to 2. That's going to be pi over 2 times e to the 4 minus e to the 0. And we get pi over 2 times e to the 4 minus 1. Now in my MATLAB, this would be your exact answer if they ask, typing like this. You have a tool to put in a fraction times, and there's a button for e, and all that kind of stuff. If they ask for the 2 decimal precision to the nearest 100, you will work this out as a decimal and then round, make sure that the third decimal, whether you increase or not, the second, right? So, yes?
One question I had was, why is e y squared the same thing as 2y expected?
Cause algebra, right? The formula. Right? That's the formula from algebra that gives us that. And then the integral divides by 2. And that takes care of this. All right. That's all the exercises for tonight. We're going to do much more tomorrow, obviously. I'm going to say bye to the stream.